Okay, so it looks like you have a great time because it's a beautiful blue sky up there, and now really fall came in suddenly. 2 weeks ago, it was hot for the last two months, 2 to 3 months for summer, and really. We never experienced such a hot summer anywhere in US or in Korea, but it was hot, right? So now everything cooled down, so it's really time for what? Time for studying hard. Then you can really have some great mileage. You know, as you study hard, really concentrate, then you will have also great time. And next week is of course Chuseok, and as you notice, I didn't really assign any homeworks, but I just mentioned to you a couple of times, think about your term project. Think is most important. Think and take a time and look at yourself, what you're doing is very, very important. I always mention to my lab students, if you don't be careful, you will just keep moving and keep moving, but without knowing what direction you are heading, and without knowing what's out there. That's very dangerous, okay? So always, that doesn't mean that don't go too fast, sit back, relax, watch TV. No, it's not. So once in a while, I want you to sit back and check out where you are and what you're doing, what direction you are going. So that's a very good measure, okay? And not only concentrate to study in your major field, but also sit back and read other materials which you really enjoy. Just take off your mind away from your major field, then spend a little bit time, then come back, okay? So here for, this is kind of a second week, and today I like to finish the chapter 2.1, that's just the beginning, but through this really introduction, get a feel on the explosions. So that's kind of important. And Friday, as time permit, I'll check to my students, Dongman, about that U571, the movie clip. Then I'll show you some really explosion in underwater actual phenomena with your basic, very small knowledge. You should be able to, God bless you, to identify what the explosion in the water is, okay? So that will conclude the really introduction, which is 2.1. Then after you come back Chuseok, then we'll do 2.2, which is really conservation law, which you really learned, I'm pretty sure, when you took something like intermediate fluid mechanics or beginning of fluid dynamics. because that's the whole basis of ship shock analysis. So it's hiding a little bit behind it, but conservation law, without that conservation law, you can solve many class of underwater shock problems. So that's what we're going to learn. So that's the direction we're going to moving on. So last Monday is continuation of Monday's talk. As you see, there are a lot of bullet items. Don't overlook. I want you to read. I'm going to just spend a little bit time with you today. Then get your feel on it. Explosive do not usually have a high energy content of ordinary fuel. What does it mean? It said, do not have high energy content of ordinary fuel. Does not content energy. Content does not have high energy content. The explosion is rather concentrated to what? Hassan, to what? Power. So fuel itself has really has connected directly to energy, but explosion is connected to the power itself. So power is a time rate change of the energy. However, it said rate of energy release, time rate change of energy, right? So that's a power. During the explosive chemical reaction process results in great the destructive the power. Fuel release energy via combustion, which is a burning, which is a relatively slow the process. So burning process is the speed is of course proportional to the function of the pressure, but that happens below the acoustic speed. If it happens in the water acoustic speed. If it's happening in the air acoustic speed. What's the air acoustic speed? What's the value? 300. What's the water? What's the water louder? 1500 meter per second. So divided by about 4.5, then you will get the acoustic speed in the air. So the fuel release energy via combustion by the burning, which is a relatively very slow process. Does it provide sufficient time for the energy to transfer into the outer medium by means of the heat conductions, radiation, and non-destructive the mechanical process? However, when you confine the volume, then what happens? Then it generates kind of a more power release, like a bullet, as I mentioned. By the burning of the gunpowder, then it is confined in the canister, small canister, and it just pushes the bullet out. So when you confine the volume, it generates higher. The energy is due to the burning. Explosive, the reaction occurs within nanosecond, which confine all of the energy to a small volume, the volume of the explosive. Hence, the energy does not have a time to escape. Then time, thus, even though explosive has less energy to release than the fuel. It releases it so fast that the energy contained in the given volume is extremely large. That's the reason explosive is so destructive. When I say nanosecond, so when I say it happened in the nanosecond, all this kind of the talks I'm doing, when you need a judgment by looking at the data you analyzed or you acquired through the testing, you should develop the kind of the to make a right decision whether the data is good or bad. Sometimes you are busy to calculate for simulation, for example, the explosion result and all that, then you don't have right now, until maybe at the end of the semester, you don't have a really decision power whether that data is correct or not. So everything, every little thing is built up. So here, this is a time t, and this is a pressure. So, for example, the explosion occurs right here. Then this is a target, okay, target in the waters, whatever. Then as at the time of explosion, then shock wave will propagate and hit the target. Then as I sit here, then I feel the explosive pressure, shock pressure is coming at me and passing by. So then if I draw no longer like this. I'm going to start from here, then move up, then draw like that. So what's this pressure would be? Anybody can feel? Before I draw the pressure time versus, this is not very good chalk. Before I draw like this, did I? Hey, don't watch me, look at me like that. That's what I did. Then nobody asked why it starts from 0. Now I draw the pressure profile, pressure time history, like this. Like that. My question is, what's this? This is non-zero. 0 is here. This is non-zero pressure. I said that this is explosive. This is a target. Then water could be way up there. What would be that pressure? Water pressure? Water depth. So this is a pressure. This is a pressure. Let's say P naught. Oh, this is good. P naught. So P naught, this is look like a static pressure, right? Caused by louder. You have to learn to speak up English. It's a little bit awkward, but let's speak up. Who cares in the class whether you speak correct or broken English? We don't care. You have to speak up, louder. Okay? What kind of the static pressure is that? As Gusto, right? Gusto said, hydrostatic pressure. Hydrostatic pressure. So the charge is here. I said that this is free surface. So this is the depth D, and of course that much the depth will generate hydrostatic pressure. What's the hydrostatic pressure if depth is D? Rho GD is what the hydrostatic pressure is. So if I say pressure, hydrostatic pressure, which is rho G D. Rho is what density? Rho is mass density of the fluid, right? And D. And always you have to put the correct unit. Metrics is much easier than US gravitational unit. So that's all. That's all the pressure. This is. I'm sorry. Jeez, I'm sorry. We are dealing with what? This is explosive. This is explosive, right? And target is here. This is a target. So gauge or target. So sometimes you say gauge or target. And the depth is, this is the depth D. Okay, sorry. That's our point of interest, right? So that's what rho GD. And the other pressure is atmospheric pressure, right? 1 bar. So another pressure is atmospheric pressure, PA. So P naught over here is P naught is pH plus P atmospheric pressure. So this is what this P naught is. Everything's all calm. So quiet. When you ride a big ship, cruise ship, it's not that quiet. Like a naval ship, I ride the aircraft carrier for a week. I ride the frigate for a week. Everything, when the ship is out in the horizon, everything's so quiet. And then nothing happens, so quiet. That pressure is what this point will experience. Then what happens? When the explosion occurs, it's bang! Sudden pressure rises up there. And even you can calculate this time, let's say T1 from 0. How? If I say from here to here, this is a distance r, then acoustic velocity in the water, let's say C naught, then you can compute the time from the time of explosion, bam, that's 0 time, then shock wave will move, hit the target, right? That time, let's call T1, you can compute the T1 as we did before. T1 is equal to what? C? So you can compute that, T1. Then shock wave will move with the speed of the C naught. C naught, don't confuse, nothing to confuse. You can use in naval ship shock analysis and design course the acoustic velocity in the water. At the beginning, when at the time of explosion, that you can use a detonation speed, which is something like 8,000 meters per second, but it converges into the acoustic speed so fast. So our interest is not in the vicinity of explosive. I don't have any interest on that. Navy doesn't have interest on that. Why? This is a ship. I repeat the same thing I told you over and over again. This is the ship, and small explosive detonate right in the vicinity of the ship, then what happened? It will puncture the hull anyway, right? If it's a submarine, if the depth charge explode very next to the submarine, then what happened? It will sink the ship, may sink the ship, may not sink the ship. The reason I'm saying is, it's all compartmentized. Okay, it has doors everywhere, right? Sealed, water sealed the door. When some compartment are flooded, it may not propagate through other compartment, then loss is there, but not the whole ship, not the whole boat. Okay? So you have to pray hard. An explosion occurs very next to the target. Nothing to prevent. You have to prevent to have such a situation. You have to prevent. There are technology around it. So here, well, anyway, I forgot where I stopped. But anyway, so this is a duration the shock wave hit the target. Then now I almost put this really straight up. Then it's a kind of a P max. In my note, sometimes I use a P naught. You have to be careful. So I'm using right here, P naught is the maximum, the static pressure, okay? Then I can draw the straight up, because the explosive shock wave hit the target. Straight up is not. Pay attention on this. I said whole explosion process happens in nanosecond. When I say nanosecond, that's what I'm trying to explain. This should not be really straight up, but it's a very, very good approximation. If I just draw a little bit correct sense, I would rather say this is a straight up, a little bit offset. Exaggerate a little bit, okay? So this could be maybe 1 or 2 nanosecond. How do you write nanosecond? Nanosecond is 10 to the minus 9 second. That much is 10 to the minus 9 second, okay? Which means visibly impossible to recognize it. So you can use as a straight up without such a deviation. So of course this is a P max. Then for the conventional explosive or chemical explosive, then what happens? It's going to come straight down, exponential decay, coming down. I would repeat this phenomena a few times. It's going to converge down to 0. Not really. I'm sorry, I confused with others. It's not going to converge down. Should I say, not that? It should converge down, approach here. Because when I talk rarefaction wave, I'll show you it's coming down below. But right now, just the free field. And this is exponential decay. Exponential decay means this is P max times e to the minus some alpha t. Exponential alpha, this alpha is some factor. Alpha is some factor, which I'm going to tell you a little bit later. So it's exponential decay. Whole exponential decay here, then just converge to P naught. This whole process, I could say this whole process is about 304 millisecond. 304 millisecond means millisecond is 10 to the minus 3, right? So 1 millisecond. So 3 to 4 millisecond, which means this is 3 to 4 multiply 10 to the minus 3 seconds. Very, very fast. In other words, everything is, for the explosion, everything is done within 3 or 4 seconds. The Cheonan incidence, everything is done in less than around 1 second. Done. So fast. You can't stop so fast. So that's I'm just talking shock wave propagation. I haven't talked about the gas bubble oscillation. This two item is most important. And for some people who claim he is expert in the explosion, some, not all, some, their thought and understanding is not clear. So you have to really, I just mentioned the shock wave propagation here. And one more. So you have understanding. You know, sometimes when you read papers and all that, you're dealing with the nanosecond duration. Sometimes you look at the millisecond duration. That's what the time we are dealing with. And this is now, this phenomena is combination of two. This is a P naught. This is a total P. This is a static pressure. You have a system, structure system, mechanical system. If it is subjected to the static pressure, then you can compute all the static response, right? Your interest is a dynamic response, right? And for the ship shock situation, you are mostly dealing with the linear system. Linear elastic analysis is what you would involve. And when damage occurs, permanent set occurs due to the shock wave or explosion, then you are dealing with a nonlinear system. Okay, but mostly you are the ship shock trial stuff, you are dealing with the linear analysis system. You can combine this with this. It's a combination of two, right? So you can separate static analysis. You know how to handle dynamics. You don't know yet. That's what you wanna learn. So this P here, this is a P. This P here, P. This is absolute pressure. This is absolute pressure. Total pressure or absolute pressure. Okay, this is absolute pressure. But here, if I draw the if I draw here, over here, oh, this is a 0 here, right? Listen carefully here. So this is one way, okay? But here, I'm going to shift my axis from here to here. I'm going to move this axis to here. So I can draw this axis now. This is a T. I can do that, right? And also, I can shift this guy, this vertical axis, to here. Then I can draw this. Rather than handling this and this, I can just get down to T, to P right there. And if you do that, what would be the pressure? This pressure is, this P is really total P minus P naught. Isn't it, right? Because the static pressure is out, just to delete it. I have no interest because I can handle that separate. This is called the gauge pressure. This pink, okay, this is gauge pressure. I'm talking this again and a couple more times, okay? That's a gauge pressure. What does it mean? What does it mean? What's the use of it? What's the use of it? What's the use of it? The gauge pressure. In the experiment, on the explosion experiment, I have free field. Okay. Then let's say the gauge, the pressure gauge I mentioned to you is about that high. Okay, about 6 centimeters that high, very flimsy. I don't have any sample here, but it's a flimsy that in measure the pressure when shock wave hit it. And you can just, this is what I'm going to do hopefully toward the end of next year, gauge. This is a gauge. For this gauge, I'm going to say simply, I'm going to say this is gauge. It's a gauge. Hook up to the to the gauge. Then as it goes deeper, it will register in the measurement instrument. As it goes down, it records the depth which related to the pressure, right? Rho G, D, right? This is higher. So let's say this is the depth. This is the depth, the D. Then initially it registers something like rho GD, the pressure in the gauge. That's the static pressure. So to measure the dynamic pressure at the time of explosion, I don't need this. We know it. So I'm going to reset the gauge to 0. At the beginning, the gauge, this is 0. The needle, this is, at the beginning, needle is showing right there. Then I reset the gauge to back to 0, right in this depth. Then I conduct the testing. Then when whatever it registered during the testing is going to be what? Dynamic pressure, right? Dynamic pressure, because in the total pressure, I delete rho GD. So this is a pressure that gauge pick up, which is dynamic pressure. This is what exactly this curve means. Just read off the static pressure. Also I shifted this time axis, vertical axis down to here. So you count, this is all introduction, so I put everything, but now in chapter 2, rest of the chapter 2 and 3 is sort out everything. So here, so you have explosive here, you have a target right there. So as a shock wave hit it, and it takes that time T1, okay? So I don't have to set the inertia frame right there. But this is, we know what happened here. Just the shock wave propagate. So I'm going to set the frame right there, saying that when explosion occurs, that's a time 0, rather than saying T1. So equation-wise, whether it makes sense or not, okay, I'll tell you. So usual P time T is equal to P max e to the minus T minus T1 some constant theta. I'm going to just say that without going into deep, okay? Theta is some constant. It's called the decay constant, but I'll tell you, just some constant, okay? Then when time, this is time T1. Okay, so over here it said T must be time T1. If T is below T1, shock wave is somewhere here. Didn't get down to the target yet. Okay? So reference time T equal to 0 is the time when the explosive detonates. But I can, so if I just relate that into frame, that frame is this, okay? This, that. T has to be greater than this, T1. Otherwise nothing happens. But now to shift into the pink, so I can say that PT is equal to, P max doesn't change, e to the minus t over theta. So here t has to be greater and equal to 0. So you start counting then from here down here. Got it? Just to put everything together, sometimes work, but eventually everything should work. For the water, dynamic property of the water, we're gonna deal as homogeneous fluid with no shear stress capabilities. Homogeneous fluid. When you're dealing with whole ocean environment, with a 10,000 meter, it's not homogeneous. It has layers of water with a different characteristics. But we are dealing with the water which in the range of ship and submarines in operation. For that depth, you don't have to worry about the change in acoustic velocity in the water. It's all homogeneous. Okay, you don't have to worry about the layers of water. So it's homogeneous. You can assume the wave propagating speed, which means acoustic speed in the water, which is about 4,900 degrees at 18 degrees Celsius. That's really most common temperature we love. 18 degrees to 20 degrees is the best. And of course, velocity is dependent on pressure magnitude, but you don't have to worry about the function, the acoustic speed in the water as a function of pressure. You don't have to worry. Okay, you don't have to worry about of course, temperature. You have to worry because like Arctic water, South Pole, North Pole, even during summer, Indian Ocean would be something like 90 degrees Fahrenheit. 90 degrees Fahrenheit is in Celsius scale, what would be it? Celsius. 5/9, you have a formula there, F minus the 32, so 60, about 30 some degree, 35, 36 degree, but Arctic Ocean is way below that India. So temperature dependency is there. What do you think? As the temperature rises, acoustic speed rises, yes or no? Yes? Temperature rises, acoustic speed rises. All the equation is in chapter 3, which you haven't got it yet, but you will get it. So, and we're going to deal with two different wave of propagation. One is a spherical wave. The other one is a plane wave. So plane wave the shock wave, well, at the time of detonation of a spherical charge, then of course it will grow. Then shock wave front is a sphere shape, is. So as it grows and grows, total energy is a constant. So as it grows, surface grows, right? Surface grow. As the surface grow, the energy per unit area of the shock wave, the shock wave front is getting smaller. Is proportional to 1 over r. R is the distance between the charge and target. So as it grows, pressure is coming down naturally. But as it really grow, big charges really grow, then the curvature of the shock wave front is approaching flat. Right? It's so big, small change, you can't really say change in the pressure, because it's almost a flat nuclear explosion. It's really flat. If it's really spherical, a shock wave front, everything killed away. There is nothing to save. So you have to be miles and miles and miles away to be survived. So that situation is a plane wave. You don't have to think about the change in the shock wave front pressure. So here, plane wave, no change in magnitude or shape, is a 1D. For the conventional explosions situation, all you can think of is really far, charge source is really far away. If it's really far away for conventional explosion, then what happens? The pressure is very small, you may not need to consider. So, but theoretically, plane wave and also the spherical wave. But also you can make a plane wave artificially by setting the line charge, let it detonate simultaneously. Then shock wave is plane wave. Spherical wave amplitude, when I say amplitude decays, the pressure amplitude decays, right? And the pressure wave in the reacting explosive begins outward motion of the water, of course, right? Duration of the shock wave is a millisecond. As I said, the whole thing goes about 3 to 4 milliseconds. Everything is done. Shock wave, okay? When you're getting into bubble motion is really different from the shock wave. Shock wave is gone, then bubble oscillate. Bubble oscillate duration of 1 to 2 seconds. That's what you have to worry. But shock wave dealing 3 to 4 milliseconds. And explosion pressure, nanosecond. Slight change of the pressure. I think I'm going to stop right here. And shock wave front is very steep. The shock wave front is discontinuous. You can say straight up steep shock wave. And Friday I'm going to talk really getting into bubble. That's all you have. When you say excitation mechanism, basic type, one is a shock wave, incident shock wave. Another one, bubble motion. The secondary shock wave caused by gas bubble. That's what you do. And my lab the students, they're all working on gas bubble and shock wave, all that. So we'll continue on Friday. Then we'll complete the chapter 2.1. Okay.